Hello friends, in today's discussion we shall be talking about the TTL subfamilies in terms of their internal structure, characteristics and parameters. TTL as outlined in previous lecture stands for transistor logic. It is a logic family implemented with bipolar process technology that combines or integrates NPN transistors, PN junction diodes and diffused resistors in a single monolithic structure to get the desired logic function. The NAND gate is the basic building block of this logic family. Standard TTL. The figure here shows the internal schematic of a standard TTL NAND gate. It is one of the four circuits of 5400/7400, which is a quad 2 input NAND gate. Transistor Q1 is a 2 emitter NPN transistor, which is equivalent to 2 NPN transistors with their base and emitter terminals tied together. The two emitters are the two inputs of the NAND gate. Diodes D2 and D3 are used to limit negative input voltages. When both the inputs are in the logic high state as specified by the TTL family, the current flows through the base collector PN junction diode of transistor Q1 into the base of transistor Q2. Transistor Q2 is turned on to saturation with the result that transistor Q3 is switched off and transistor Q4 is switched on. This produces a logic low at the output with VOL being 0.4 volt maximum when it is sinking a current of 16 milliampere from external loads represented by inputs of logic functions being driven by the output. The current sinking action is shown in figure here. Transistor Q4 is also referred to as the current sinking or pull down transistor. Diode D1 is used to prevent transistor Q3 from conducting even a small amount of current when the output is low. When the output is low, Q4 is in saturation and Q3 will conduct slightly in the absence of D1. Also, the input current IIH in the high state is nothing but the reverse biased junction diode leakage current and is typically 40 microampere. When either of the two inputs or both inputs are in the logic low state, the base emitter region of Q1 conducts current, driving Q2 to cut off in the process. When Q2 is in the cutoff state, Q3 is driven to conduction and Q4 to cut off. This produces a logic high output with VOH minimum equal to 2.4 volt, guaranteed for minimum supply voltage VCC and a source current of 400 microampere. Transistors Q3 and Q4 constitute what is known as a totem pole output arrangement. In such an arrangement, either Q3 or Q4 conducts at a time depending upon the logic status of the inputs. The totem pole arrangement at the output has certain distinct advantages. The major advantage of using a totem pole connection is that it offers low output impedance in both the high and low output states. In the high state, Q3 acts as an emitter follower and has an output impedance of about 70 ohm. In the low state, Q4 is saturated and the output impedance is approximately 10 ohm. Because of the low output impedance, any stray capacitance at the output can be charged or discharged very rapidly through this low impedance, thus allowing quick transitions at the output from one state to the other. Another advantage is that when the output is in logic low state, transistor Q4 would need to conduct a fairly large current if its collector were tied to VCC through R3 only. A non-conducting Q3 overcomes this problem. A disadvantage of the totem pole output configuration results from the switch off action of Q4 being slower than the switch on action of Q3. On account of this, there will be a small fraction of time of the order of a few nanoseconds when both the transistors are conducting, thus drawing heavy current from the supply. Other logic gates in standard TTL. As discussed earlier, the NAND gate is the fundamental building block of the TTL family. In the following sections, we will look at the internal schematics of the other logic gates and their similarity to the schematic of NAND gate discussed in detail earlier. Figure here shows the internal schematic of a NOT gate in the standard TTL family. The schematic shown is that of one of the 6 inverters in a hex inverter. The internal schematic is just the same as that of the NAND gate, except that the input transistor is a normal single emitter NPN transistor instead of a multi emitter one. NOR gate. Figure shows the internal schematic of a NOR gate in the standard TTL family. The schematic shown is that of one of the 4 NOR gates in a quad 2 input NOR gate. On the input side, there are 2 separate transistors instead of the multi emitter transistor of the NAND gate. The inputs are fed to the emitters of the 2 transistors, the collectors of which again feed the bases of the 2 transistors with their collectors and emitter terminals tied together. The resistance values are the same as those used in the case of NAND gate. The output stage is also the same totem pole output stage. The only input condition for which transistor Q3 and Q4 remain in cutoff is the one when both the inputs are in logic low state. The output in such a case is logic high. For all the other input conditions, either Q3 or Q4 will conduct, driving Q6 to saturation and Q5 to cutoff, producing a logic low at the output. AND gate. Figure shows the internal schematic of an AND gate in the standard TTL family. The schematic shown is that of one of the 4 AND gates in a quad 2 input AND gate. In order to explain how this schematic arrangement behaves as an AND gate, we will begin by investigating the input condition that would lead to a high output. A high output implies Q6 to be in cutoff and Q5 to be in conduction. This can happen only when Q4 is in cutoff. Transistor Q4 can be in cutoff state only when both Q2 and Q3 are in conduction. This is possible only when both inputs are in logic high state. Let us now see what happens when either of the two inputs is driven to low state. This derives Q 2 and Q 3 to the cutoff state, which forces Q 4 and subsequently Q 6 to saturation and Q 5 to cutoff. OR gate. Figure here shows the internal schematic of an OR gate in standard TTL family. The schematic shown is that of one of the 4 OR gates in a quad 2 input OR gate. We will begin by investigating the input condition that would lead to a low output. A low output demands a saturated Q 8 and a cutoff Q 7. This in turn requires Q 6 to be in saturation and Q 5, Q 4 and Q 3 to be in cutoff. This is possible only when both Q 1 and Q 2 are in saturation, that is, both inputs are in logic low state. This verifies one of the entries of the truth table of the OR gate. Let us now see what happens when either of the two inputs is driven to high state. This derives either of the two transistors Q 3 and Q 4 to saturation, which forces Q 5 to saturation and Q 6 to cutoff. This drives Q 7 to conduction and Q 8 to cutoff, producing a logic high output. Exclusive OR gate. Figure shows the internal schematic of an XOR gate in the standard TTL family. The schematic shown is that of one of the 4 XOR gates in the quad 2 input XOR gate. We will note the similarities between the circuit and that of an OR gate. The only new element is the interconnected pair of transistors Q 7 and Q 8. We will see that when both the inputs are either high or low, both Q 7 and Q 8 remain in cutoff. In the case of inputs being in the logic high state, the base and emitter terminals of both these transistors remain near the ground potential. In the case of inputs being in the low state, the base and emitter terminals of both these transistors remain near VCC. The result is conducting Q 9 and Q 11 and non-conducting Q 10, which leads to a low output. When either of the inputs is high, either Q 7 or Q 8 conducts. Transistor Q 7 conducts when the input B is high, and transistor Q 8 conducts when the input A is high. Conducting Q 7 or Q 8 turns off Q 9 and Q 11 and turns on Q 10, producing a high output. This explains how this circuit behaves as an XOR gate. AND or invert gate. Figure shows the internal schematic of a 2 wide 2 input AND or invert or AND NOR gate. The schematic shown is that of one of the 2 gates in a dual 2 wide 2 input AND or invert gate. The 2 multi-emitter input transistors Q 1 and Q 2 provide ANDing of their respective inputs. Drive splitters comprising Q 3, Q 4, R 3 and R 4 provide the OR function. The output stage provides inversion. The number of emitters in each of the input transistors determine the number of literals in each of the minimum terms in the output sum of products Boolean expression. how wide the gate is going to be is decided by the number of input transistors, which also equals the number of drive splitter transistors. Tri-state gate. A tri-state gate has three output states, namely the logic low state, the logic high state and the high impedance state. An external enable input decides whether the logic gate works according to the truth table or is in the high impedance state. Figure shows the typical internal schematic of a tri-state inverter with an active high enable input. When the enable input is high, it reverse biases diode D1 and also applies a logic high on one of the emitters of the input transistor Q1. The circuit behaves like an inverter. When the enable input is low, diode D1 becomes forward biased. A low enable input forces Q2 and Q4 to cut off. Also, a forward biased D1 forces Q3 to cut off. With both output transistors in cutoff, the output essentially is an open circuit and thus presents high output impedance. Floating and unused inputs. The floating input of TTL family devices behaves as if logic high has been applied to the input. Such behavior is explained from the input circuit of a TTL device. When the input is high, the input emitter base junction is reverse biased and the current that flows into the input is the reverse biased diode leakage current. The input diode will be reverse biased even when the input terminal is left unconnected or floating, which implies that a floating input behaves as if there were logic high applied to it. As an initial thought, we may tend to believe that it should not make any difference if we leave the unused inputs of NAND and AND gates as floating, as logic high like behavior of the floating input makes no difference to the logic behavior of the gate as shown in figure A and B. In spite of this, it is strongly recommended that the unused inputs of AND and NAND gates be connected to a logic high input as shown in figure C, because floating input behaves as an antenna and may pick up stray noise and interference signals, thus causing the gate to function improperly. 1 kilo ohm resistance is connected to protect the input from any kind of spikes. More than one unused input can share the same 1 kilo ohm resistance if needed. In the case of OR and NOR gates, unused inputs are connected to ground as shown in figure C. A floating input or an input tied to logic high in this case produces a permanent logic high and low at the output as shown in figures A and B respectively. An alternative solution is shown in figure D, where the unused input has been tied to one of the used inputs. This solution works well for all gates, but one has to be conscious of the fact that the fan out capability of the output driving the tied inputs is not exceeded. If we recall the internal circuit schematics of AND and NAND gates, we will appreciate that when more than one input is tied together, the input loading, that is the current drawn by the tied inputs from the driving gate output in the high state is n times the loading of one input. N is the number of inputs tied together. So friends, here we come to the end of our discussion in this lecture, and therefore we sum up. We learnt about the TTL subfamilies in terms of their internal structure, characteristics and parameters. It is a logic family implemented with bipolar process technology that combines or integrates NPN transistors, PN junction diodes and diffused resistors in a single monolithic structure to get the desired logic function. The NAND gate is the basic building block of this logic family. So, that is it for today. See you in the next lecture with more on combinational logic. Thank you very much.